Hello everyone. Welcome to this third session under Scikit-learn series by IntelliPath. Today we are going to discover one of the broader areas of machine learning problems, that is classification. But before we get started with that, make sure you guys hit that subscribe button so that you'll never miss any update from IntelliPath YouTube channel. First of all, let me take you guys through the agenda for this session. We'll begin this session on a friendly note by talking about what classification problem is, and we'll try to build a basic programming intuition for the same with one basic example. Once we understand the concept of classification, we'll talk about a few technical machine learning terminologies related to classification. Finally, we'll dive into different classification algorithms that scikit-learn offers. Here, we'll just take introduction about these algorithms. I hope that you guys are clear with the agenda. So, without wasting any time, let's dive into the first topic of this session, that is, what is classification in machine learning? If we talk about classification in real life, what it simply means is dividing different sets of objects into different classes based on their properties or features, right? I mean, let's say you go to the market and you buy different types of fruits such as apples, oranges, and mangoes. You place all of them in a single carry bag while bringing them home. And after reaching home, you want to store them in the fridge. Here, the first thing you'll do is you'll split these fruits into different groups based on their features such as shape, texture, color, etc. And this is exactly what classification is in its very basic sense. Now, if we enter into the discussion of classification in machine learning, then let me tell you guys that classification in machine learning is very similar to the real life scenario that we discussed earlier. It's just you can visualize the features, learn them, and classify because you are cognitive people, right? But machine cannot work the same way. In case of machines, you'll have to provide machine with both features and class labels. Then it will learn the pattern and will further be able to make predictions when new data is provided. Alright. Now let me also formalize the classification term more. Guys, this classification is a process of categorizing a given set of data into classes. It can be performed on both structured or unstructured data. This process starts with predicting the class of given data points. The classes in the context of machine learning are referred to as targets or labels. Now, to visualize how the classification is achieved, we'll dive through one very basic classification problem and we'll solve it using perceptron. Now to visualize how the classification is achieved, we'll dive through the very basic classification problem and we'll solve it using perceptron. Now to create perceptron, we don't require scikit-learn library. But guys, looking into this example, we'll be actually able to understand the basic notion of classification. Now let me tell you a little bit more about perceptron before we start dealing with the problem. So guys, we know that neural networks are composed of multiple neurons. These neurons process the provided input, assign some activation to it, and transform it into output. The basic neural network looks something like this, right? Now boil down this to a single neuron or a single layered network, then that particular network will be known as perceptron. Here is how a perceptron's logical structure look like. So as shown in this image, the perceptron takes the input x, y, z, multiplies them with weights w0, w1, w2 and applies some sort of activation to them to create output prediction that matches with given output data. Now if I have to put this whole learning in basic equation, then I'll say predicted output will be equal to x into w0 plus y into w1 plus z into w2 plus bias. Now the example that I'm going to talk about is the OR gate problem. Now this is how the OR gate transforms the output, right? Now if you provide 0 0, the output will be 0. If you provide 0 1, output will be 1. If you provide 1 0, output will be 1. And if you provide 1 1, the output will be again 1. As you can see in this table, we only have two classes, 0 and 1. And whenever both the switches are off, only then output generated by OR gate will be 0 or off. What that means is when both A and B have 0 input, then only the output will be 0. Otherwise in all cases the output will be 1. Now let's put this data into perceptron diagram available right here. Now guys, we need to figure out the weight values such that after applying an activation, our model will generate the prediction that is equivalent to given output. Let me show you guys a hands-on demonstration for the same by taking pre-configured values into account. Well guys, we have both input values and output values. All we have to do is figure out the weight values and bias such that our model will be able to make the prediction that matches with given output data, that is y. So first of all, let's import both input and output vectors. Alright. So for that purpose, I'll first import the NumPy library. After that, I will create a variable x that will store an array of data entries. The first entry will be 0 0, then we'll have 0 comma 1, then we'll have 1 comma 0 and 1 comma 1. Similarly, we'll have the output array which will store the outputs of OR gate for each case. That will be 0 comma 1 comma 1 comma 1. Now let's print both x and y as well. Yeah, here you can see that we have both x and y in our notebook right now. So let's consider some random weight values. Right now we'll consider these weight values to be 1 and 1. Okay, so let's create one more array to store weight values. Alright, and we'll print this weight as well. And as we said before, we are going to consider pre-computed values. So we have configured weight values as 1 and 1. Similarly, we'll consider bias values as minus zero point 0.5. Now guys, if you put these pre-computed values into the equation that we discussed earlier, you'll be able to formulate prediction that will accurately match with your y or the output data. Alright, so let me show you how that is done with the help of program. Now I will create the prediction list where we'll store our predictions. After that, we'll take a for loop and iterate through our input vector, that is x, and we'll calculate the predicted value and we'll name it as y underscore hat, and it will be nothing but the dot product of a comma w, and we'll add bias to it. Alright, now the only thing that is left is passing our predicted value through some sort of activation. Alright guys, so we'll need to create one manual function for that, but before that let me append that activated value to our prediction list. So I'll do that here. Now we'll create that activation function, def activation, and we'll pass z as an argument. So basically we'll be using relu as our activation function. So basically what we'll do is when our predicted value will be greater than 0, then it will belong to class 1, otherwise it will belong to class 0, because we have used bias as minus 0.5. So when we pass 0 0 as input and it will get multiplied with weight matrix 1 1, then the output that we'll get will be 0, and if we subtract 0.5 from it, then we'll get minus 0.5, which will be a negative value. So hence what we'll do is we'll put if z is greater than or equal to 0, then return 1, else return 0. So this is our activation guys. So let's run this block. Alright, now let's run this block as well. Alright, so now all we have to do is print this predictions. So here you can see that the predictions that our model has made are are entirely similar to our given output data. Alright, so this is how the perceptron works when we have pre-configured values. Now let's move back to presentation and learn how Perceptron can actually learn these weight values and biases all by itself. So guys, again we will be using that OR gate example to understand how this classification works, alright? So basically all we need to do is understand the learning process behind Perceptron. So basically what we'll do is we'll understand the error that we are getting in our prediction, and then we'll propagate that error backwards to our perceptron. Alright, so how we can do that? Well, what we'll do is we'll change our weights during the every epoch that we train our model with. Alright, so with each epoch we'll have new weight value inserted into our perceptron model, that will be equal to old weight minus learning rate into gradient of error with respect to the weight. So what is gradient, guys? Gradient is nothing but partial derivative of error with respect to the weight, and error will be again output minus the predicted output, or what we call as y hat. So error will be y minus y hat, and its partial derivative will be del y minus y hat divided by del w. Alright guys, so this was the mathematical intuition behind our learning procedure. So let's visit the code editor and directly understand how we can interpret all of these mathematics into our programming interface. Alright, so guys, first of all we'll import few libraries, that is math library and numpy library. Anyway, we have imported this library previously as well, but still I'll import it again. Now the next step will be defining epochs that we want to give to our model. So right now we'll set some random epochs. Let's say we want to train our model over 100 epochs. Alright, so we'll set epochs as 100 and learning rate, that is alpha, equal to 0.2. So guys, basically these are the hit and trial values. You can try with 50 epochs as well, and alpha as 0.7 or 0.4 as well. Alright, so let me run this block as well. Now what I'll do is I'll generate value for w0, and it will be a random value because we don't want to assign any value, pre-configured value by ourselves. So we'll take a random value from system itself. Similarly for w1 and w2. Alright guys, now we'll print this initial weights. W0 equal to w0, then w1 equal to w1, and w2 equal to w3, sorry, w2. Alright, and we'll run this block. Now here we have random weight values. Alright, and if we take partial derivative of these values, then the return we'll get will be 1. Alright, so initially the delta w, that is partial derivative of weight, will be 1. So del w0 will be equal to 1, del w2 will be equal to 1, and similarly del w1 will be equal to 1. Well guys, moving ahead, what we are going to do is we are going to specify our training data. In this particular sample, what I'm doing is I'm providing input of 3 switches to our AND gate. So instead of taking 2-phased input, it will take 3-phased input now. Alright, so that will have more samples to run our algorithm with. Alright, so the train data set will be 0, 0, 0, then 0, 0, 1, then 0, 1, 0, then 0, 1, 1, then 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. Alright. So right now we have 1, 2, 3, 4, 5, 6, 7, and finally we'll have 1, 1, 1. Now again, as we are using OR gate, the output will be np.array 0, 1, 1, 1, 1, 1, 1, 1, 2. Alright. So this will be the output vector. Now we need to convert this into array as well. So for that purpose, we'll use adds array method. So train data will be equal to np.adds array, and we'll pass train data temp as an argument. Alright, so let's run this block. Now I'll print both train data and our label, that is OP. Alright guys, so we have our training data configured. Now all we have to do is put these values into our equation that we have discussed in previous slide. So that equation, I'll write that equation here. That is y equal to x into w plus b. Alright. Now we'll do that in next block. So how we will be doing that? First we'll define the bias. Let's set it at 0 because we want to learn weights in proper manner. Alright. So we'll set bias at 0. Then we'll start iterating through the epochs. Now inside these epochs, what we'll do is basically we'll iterate our training data, right? So for x in train underscore data, we'll create the resultant, or let's say it y hat itself. Y hat equal to w0 into x0 plus w1 into x1 plus w2 into x3, and we'll add our bias to it. Alright, so this is what the equation that we have written above. Now we'll apply the activation here itself. Now if result is greater than or equal to 0, we'll set our activation as 1, and otherwise we'll set our activation as 0. Alright, now the next step will be calculating the error. I told you guys that error will be the output minus the prediction that we have made. Alright, so activation will be the prediction here, but guys, iterate this output list as well. So for that purpose I need one more independent variable. So I'll define j is equal to 0 as new independent variable, and I'll use it to iterate the label data. Alright, so this will be our error. Now the next step will be calculating the gradient. Okay, so the gradient for w0 or weight 0 will be equal to alpha into x0 into error. Alright, now similarly del w1 will be learning rate into x into error, and similarly del w2 will be equal to alpha into x2 into error. Alright, and the new weight will be the previous weight plus the change in weight, that is del w0. Now this will prevail for all other weights as well, that is weight 1 and weight 2. Alright, now we want to keep iterating through these epochs, so we'll set j is equal to j plus 1, and if you guys want we can print error after each epoch. Alright, so print epoch I plus 1 comma error, and similarly we can also print the derivative weights. Alright, del w0, del w1 and del w2. Next we'll get out of these loops and we'll also print the final weights. W0 will be equal to W0, W1 will be equal to W1, and W2 will be equal to W2. Alright, so let's run this code. Well, there is error somewhere. Index 3 is out of bound for axis 0 with size 3. Okay, we have mentioned x3 over here, but we only have 2, so we'll change that. Name res is not defined. Okay, we have y hat here, y underscore hat, and we'll run it. Okay guys, now I hope this learning process is clear to all of you guys, and you are clear with how we can transform the input data towards the label. Alright, now moving forward, we'll talk about few technical terms related to classification. Well guys, basically in machine learning predictive classifying, we have 4 different types of problems. Those 4 types are binary classification, multi-class classification, multi-label classification, and imbalance classification. First, let's talk about binary classification. Binary classification problems often require 2 classes, one representing the normal state and the other representing the aberrant state. For instance, the normal condition is not spam while the abnormal state is spam. Another illustration is when a task involving a medical test has a normal condition of cancer not identified and an abnormal state of cancer detected. Class label 0 is given to the class in normal state, whereas class label 1 is given to the class in abnormal condition. We just saw the programming implementation of a problem that belongs to the same category, the OR gate problem. Now the next type we have is multi-class classification. The multi-class classification does not have the idea of normal and abnormal outcomes in contrast to binary classification. Instead, instances are grouped into one of several well-known classes. In some cases, the number of class labels could be rather high. In a facial recognition system, for instance, a model might predict that a shot belongs to 1 of 1000 or 10 of 1000 faces. Text translation models and other problems involving word prediction could be categorized as a particular case of multi-class classification. Each word in the sequence of words to be predicted requires a multi-class classification, where the vocabulary size determines the number of possible classes that may be predicted and may range from tens of thousands to hundreds of thousands of words. Isn't that fascinating, guys? Now, the third up is multi-label classification. Multi-label classification problems are those that feature 2 or more class labels and allow for the prediction of 1 or more class label for each example. Think about the photo classification example. Here, a model can predict the existence of many known things in a photo, such as person, apple, bicycle, etc. The example of this will be Google Lens program, which is implemented by Google. This algorithm can detect the objects available in front of your camera, alright? The example that I just talked about greatly contrasts with multi-class classification and binary classification. One more thing, guys, this multi-class classification greatly contrasts with binary classification because both of them has single class label for each occurrence. Now, multi-label classification problems are frequently modeled using model that forecast many outcomes, with each outcome being forecast as a Bernoulli probability distribution. In essence, this approach predicts several binary classification for each example. Alright. Finally, we have imbalance classification. This term describes classification problems where the distribution of example within each class is not equal. That means every class will have different data distribution. A majority of training dataset instances belongs to normal class while a minority belong to abnormal class, making imbalance classification task binary classification task in general. The examples of this task composes clinical diagnostic procedures, detection of outliers, and fraud investigation. Although they could need unique methods, these issues are modeled as binary classification jobs itself. By oversampling the minority class or undersampling the majority class, specialized strategies can be employed to alter the sample composition in the training dataset for imbalance classification problems. Now, next, let me also tell you about learner type terminologies. So, we have lazy learners and eager learners. Let's first understand lazy learners. Lazy learning refers to the machine learning processes in which generalization of the training data is delayed until a query is made to the system. This type of learning is also known as instance based learning. Lazy classifiers are very useful when working with large datasets that have a few attributes. Learning systems have computation occurring at two different times, training time and test time. Training time is the time before the test time. During training time, the system derives inferences from training data to prepare for the test time. Here, less time is spent on training, but more time is spent on predictions. Some of the common examples for this type of learners are KNN and case based reasoning. Then the eager learners. Before obtaining a test dataset, eager learners build a classification model using training dataset. They spend more time studying and less time predicting. Some of the examples are artificial neural network, naive Bayes, and decision tree. Next, we'll talk about classification algorithms in machine learning. Guys, you can apply many different classification methods based on the dataset you are working with. It is so because the study of classification in statistics is extensive. Moving forward, we are going to learn about scikit-learn classification algorithms one by one. The first scikit-learn classification algorithm we are going to talk about is logistic regression. Basically, this algorithm is a supervised learning classification technique that forecasts the likelihood of a target variable. Data can be coded as either 1 or yes, representing success, or 0 or no, representing failure. The dependent variables or the continuous data points can be predicted most effectively using logistic regression. When the forecast is categorical, such as true or false, yes or no, or 0 or 1, you can use logistic regression without any doubt. The examples of this algorithm can be determine whether or not email is spam. Then we have k-nearest neighbors algorithm. The KNN algorithm assumes that similar things exist in close proximity. In other words, similar things are near to each other. Notice the image on your screens. You can observe that most of the time similar data points are close to each other. The KNN algorithm hinges on this assumption and makes predictions. KNN captures the idea of similarity with some mathematics we might have learned in our childhood, calculating the distance between points on a graph. There are other ways of calculating distance, and one way might be preferable depending on the problem we are solving. However, the straight line distance is a popular and familiar choice. Third up, we have a decision tree algorithm. Decision tree algorithm belongs to the family of supervised learning algorithms. Unlike other supervised learning algorithms, the decision tree algorithm can be used for solving regression and classification problems too. The goal of using decision tree is to create training model that can be used to predict the class or value of the target variable by learning simple decision rules inferred from the prior data. In decision trees, for predicting a class label for a record, we start from the root of the tree. We compare the values of the root attribute with the records attribute. On the basis of comparison, we follow the branch corresponding to that value and jump to the next node. Next, we have random forest algorithm. Random forest is a popular machine learning algorithm that belongs to the supervised learning technique. It can be used for both classification and regression problems in machine learning. It is based on the concept of ensemble learning, which is a process of combining multiple classifiers to solve complex problems and to improve the performance of the model. As the name suggests, random forest is a classifier that contains a number of decision trees on a various subsets of the given dataset and takes the average to improve the predictive accuracy of that dataset. Instead of relying on one decision tree, the random forest takes the predictions from each tree and based on majority votes of predictions, it predicts the final output. The greater number of trees in the forest leads to the higher accuracy and prevents the problem of overfitting. Fifth up is support vector machine algorithm. Support vector machine or SVM is one of the most popular supervised learning algorithms, which is used for classification as well as regression problems. However, primarily it is used for classification problems in machine learning. The goal of SVM algorithm is to create the best line or decision boundary that can segregate n-dimensional space into classes so that we can easily put the new data points in the correct category in future. This best decision boundary is called as hyperplane. You can look at the image present on your screen. Here, you can find out the plane like space that is distinguishing between two different types of objects, right? SVM chooses the extreme points that help in creating the hyperplane. These extreme cases are called support vectors, and hence the algorithm is termed as support vector machine. Finally, we have the naive Bayes algorithm. This algorithm is a statistical classification technique based on Bayes' theorem. It is one of the simplest supervised learning algorithms. Naive Bayes classifier is the fast, accurate, and reliable algorithm. This classifier have high accuracy and speed on large datasets. Basically, guys, this classifier assumes that the effect of a particular feature in a class is independent of other features. For example, guys, let's say we have a loan application and we want to find out if it is desirable or non-desirable. And to find that out, we have features such as his income, previous loan statements, transaction history, age, and location. Even if these features are quite interdependent, in case of naive Bayes, we consider them completely independent. And this assumption simplifies our computation much better. And that is why it is considered as naive. We have just defined all the algorithms that we have for classification in scikit-learn. Don't worry if you don't understand much about these algorithms. In near upcoming sessions, we'll talk about them in detail. For this session, that's all I have. I thank you all for being here till the end of this session. I hope this session was informative and enthralling. If you have liked this video, a thumbs up would be much appreciated. Also, if you have any concern about said concept, then please put them in the comment box below. Our 24 by 7 team of experts would be obliged to resolve all of them for you guys. Also, make sure you are subscribed to the IntelliPath YouTube channel so you never miss upcoming updates from IntelliPath.
If you want to make a career in data science, then IntelliPath has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.